The next one that I want to talk about at some length is a so-called token passing algorithm. And then if we have time left, then I want to do an algorithm that is not only explained in the book, but something that is considered important in the technical literature. So here is a specific algorithm for the following problem and using the following technique. And all of that, both of these need explained. First of all, by a token, we simply mean a special kind of message, nothing more. And on the other hand, this is going to go to this channel called the token there. That happens to be the particular choice of this algorithm. Now, by a mutual exclusion algorithm, we mean the same as in the old, the way we use all the time. So we want to have a protocol for doing the standard mutual exclusion problem, meaning we have a number of processes. All of them have their own critical sections, and the requirement of the overall requirement of the problem is that if one process is executing its critical section, then all other processes must be excluded from theirs. And that there should be no contention that will take forever to resolve, etc. So all the old mutual exclusion requirements are present here. Now, if you have implemented semaphores, distributed or not, you would have used them. That's a solution. Here, we are trying to solve that, say, a mutual exclusion problem, without using semaphores, whether they are the distributed kind or not. We are now trying to solve that problem in the presence of distributed processes, that is, let's say one process per CPU spread across. All they can do is send and receive messages. And there is no special process. Okay. And here is the overall idea of that. And once again, we have these channels. And there are helper processes as before. So this process, the helper process is the one that will let the main process to go or not go by putting in a message on the go channel. As you can see, a process that wants to go to its critical section will do a waiting for some message to appear on its own item, go channel. Okay? And we will do that only when the helper has said, has put out a message on go. And I think the rest of the stuff should be fairly clear. Remember, there is one message circulating, so to speak, like a coin, let's say, just like this token. And so this helper of yours will wait for that token to arrive there. And as long as your corresponding process is not trying to enter into a section, what would it do? Well, it would simply receive that token and give that token to the next one. So here, there is an assumption that all the processes are arranged in a circular list, in a ring. On the other hand, if this corresponding process of yours wanted to go into a critical section, it would have done that. It would have sent, in this case, the actual content of the message doesn't matter. Okay, that's why most of these, that's what these channels are. They don't have any fields at all. Just the channels are empty or not. That's all that matters. Okay, so the process will send this message and then wait for the go signal. And as you can see, once the helper receives this token and then checks if the enter channel is empty or not, in which case it empties when the enter channel is not empty, it receives this one token, one message, and therefore it should become empty, and now it does a go, and then it does the wait for the exit. And the exit is sent by other process. So effectively, we are doing the PV kind of operations here, as you can see, not using distributor semaphores or quadratic semaphores. The main assumption here is that all the processes are arranged in a circular manner, and there is this one token which will not get lost nor get created arbitrarily. So this one token, once present, keeps on circulating in the token ring. Note that as a result, if the ith process wants to enter the critical section and it just passed the token to the next one, it will have to wait that many total time units for the token to arrive back at it. Yeah.
We assume that there's some initialization process that starts the token.
Yeah. Okay. And the invariant shown here, I think this I didn't find it in the book, so I wrote it down. That you may want to take. Of course, that there is exactly one token, and if the ith process is in the critical section, it better be the case that your helper has the token. Otherwise, we violate it. Fair enough. Take it out. The next problem, the next algorithm that we are going to talk about is I typically find is difficult to understand the problem itself, not the solution. Once you understand the problem, the solution is fairly easy. This one, this mutual exclusion problem, we just did it using tokens, and as I said, if we have time, I'll show you with messages without tokens. Later on. The next problem is known as termination detection. Okay, and as I said, the context of the problem needs to be explained at some length. And you need to tell me when it is clear to you. Okay, otherwise I may wrongly assume it's fine. In the typical sequential program, how do you know that it has terminated? Well, there's a bottom, so to speak, of the entire code. And if control reaches that bottom, you know the program has terminated. And as long as there is a strict hierarchy of processes in terms of parent-child, you could use a similar thing and say a collection of processes has terminated when all the processes have. Right? So it seems an obvious enough answer to the termination problem when the processes are strictly related to each other in a particular hierarchy. The case that we are talking about in this course is not that. Here, we have a situation of processes across a network, geographically distributed. And these processes give each other work to do. And how do they give this work? They send a message saying, compute this. So they give all the relevant data and also, let us say, even the algorithm, and then the other side computes the answer. And when it is done, it will inform the giver, original giver of the problem, saying that I am done. Right? So this is the fundamental assumption that we are making here. We have a bunch of processes that are equal in terms of privilege, and they give each other jobs to do, work to do. And this work to do is given to a specific node or specific process based on some other criteria, like you have a light load, therefore you should have this job. Some other node is heavily loaded, so therefore we shouldn't give it. But these are considerations that we are not going to talk about here at all. On what basis you chose a particular node. On some basis we did. In particular, this node, which is about to accept a new job, may have thought that it is true with its computation. Okay? So it did the previous job, somebody gave it. Right now, it thinks it is done. Meanwhile, there is a job in the queue, so to speak, arriving from somebody to it. So that if somebody were to ask it, are you through? It may have said yes, only to discover a moment later that this new job arrives. Are we clear on this? So its status from, say, at least from idle to active changes as a result of receiving the message. And we have the problem of determining when is this entire network done, terminated. There's a problem with it. A physical analogy that I try sometimes and works most of the time is this. Imagine each of you are at your own home and you're all connected with telephones. And each of you is allowed to give somebody else work to do. Okay, and each piece of this work takes a certain amount of time to do. Right? And of course, the whole thing began, say, from me. Right? Eventually, I want to ask the question, are we all done? And I want, of course, the correct answer for that. Roughly speaking, we are all done when all of us are idling. Plus, there are no messages in transit. Right? And this is what we are trying to detect. Okay? And that is where the analogy of the telephone kind of breaks down. The better one to substitute there is mail, regular mail. I'm sending you a piece of job and I posted it, I mailed it, but it hasn't been delivered to you yet. Somewhere in the middle. And meanwhile, if somebody asked you, are you done? You could say yes. Correctly, of course. You are saying yes, you are done. Right? Okay. So, the problem here is we do not have any one global process which can look at all of us and then give an answer about the global state. Global not meaning that it is shared in some way, but the overall state of the system we cannot determine. The overall state of the system we want to accumulate by asking piecemeal questions of each process. Okay? So this is what we mean by termination detection. The problem statement clear? Okay. Again, we are going to assume that these processes or nodes are organized in a ring. Okay? And here is the solution for termination detection using token again and assuming that the processes are in a ring. And in order to explain this, we use these colors. These are arrays of things, one per process. And the blue means that it is idling. A process is idling. Red means a process is working on a particular job at the moment. Okay? And here is the there is a special, one of the processes we are calling it number one. Note that it is not in any other sense privileged. It is number one, whichever one you mark number one. If that is blue, then we have the following invariant. That all the processes from 1 up to this token, which is in this case being used as a number, all the processes from 1 up to the next one following the token, these are all blue, meaning these are all idle. Okay? And the channels starting from 2 all the way, modulo, this is circular as I said, ring. So modulo n plus 1, these are all empty. There are no messages waiting to be read, waiting to be received. Okay. So let's see what we do. So the first action, when this first process becomes idle, we color it blue. Okay. And we initialize the token count to 0, and we send this token to the next process. Process 1 and 2 are connected by channel number 2. And channel I connects to process number I. Alright? So, this is all that we do. Now on the other hand, if you look at the remaining processes, the actions are as follows. The ith process, when it receives a regular message, this is the non-token message, then obviously it is now beginning its job, its work, regular work. So it colors itself, regardless of whatever it was before, to red. Right? This is our intuitive meaning of the word red, that is now active. On the other hand, if it receives this token number, which is a special token, then it is going to color itself blue, because this token is arriving, meaning that it is, the setup of all of this is, the processes in this ring are set up in such a way that they receive a token or the next job only when they have computed the preceding one. Okay? So typical producer-consumer kind of setup here. You get a message. This message is either a regular message giving you a job to do, or it is a token. Once you get a regular message, you work on it. Until you are done with that work, you don't go back and do one more receive. So, given that this message it received is a token, then obviously you are done with the previous job that was given to you. So you color yourself blue, you increment the count, and you send this token to the next guy. Okay? So, eventually, hopefully this should happen. Eventually, process 1, which got the whole thing started, receives the token. Not a regular message, the token. In which case, it will ask itself, well, am I colored blue? And if so, now we are claiming, we know that the entire network of n processes is terminated. Okay, we'll argue a little bit about the correctness of that. But on the other hand, if that color was not blue, then what do we do? Well, we color it blue now. Why? Just as before, we got this token, we being number 1 process now. So we are receiving we are trying to receive a regular message and we got a token. That means we were done with the previous computation. So therefore, process 1 itself is now beginning to idle. And so it reads token to 0 and does the original sending it to the next process in the ring. So question is, why are we allowed to declare termination? Is it correct? Yeah.
I would think that it would be correct as long as you can guarantee that the channels are zero. In other words, that if process 1, say, sends a token message, that it won't, that token
that one, if you remember, way at the beginning we said so, and we said in so far as we are using these channels and the asynchronous message passing, the order in which the messages are received is exactly the same order in which they are sent. If you remember this, the last item. Given one sender and one receiver and a channel between them, the order in which things are sent is the order in which things are received. Note that we are not saying from different senders things are received in the same order. But as long as it is one sender and one receiver, this is true. Okay, so that is determination detection. And let me hear one more justification for why this is so. Why, when process 1 discovers that it is already colored blue and receives the token, that means all the network is done.
And we are assuming here that the process, the piecewise process, cannot receive the token, job message that will make color red.
Yeah.
But another process that is behind mode, who is sending this red message? They're sending it all to each other. Can they all?
They can, right. These processes being organized in a ring, they can give to the next one a job.
Only to the next one.
Only to the next one, right.
Okay.
And following this algorithm, there is one for a complete graph, which is roughly speaking similar in style. So what is the basic thing that's happening here? It kind of flushes out, right? If you send this blue token, and this blue token arrives back at you, it means that this made one complete circular trip. The color did not get changed anywhere. So therefore, all the processes have done a receive, and instead of receiving a regular message, they receive this token. Right? So if you look at this, all of these are blue. Right? So that is the overall justification for this algorithm. And let me explain the rest of the section of the chapter a bit before going on to some problem solving of CSP type things. In the asynchronous communication, you can classify a number of algorithms into these. And this is a very rough characterization. Okay, so don't read too much in them. And we are not showing the actual computation at this stage here. We are only showing the structure of the send receives. And the actual computation, for example, in the case of what we just discussed, distributed termination, we didn't show you the actual computation. We only showed the overlay on top of it. Okay, same thing is happening here. This is called a heartbeat algorithm for the obvious reasons. A given node sends information to its neighbors. In our ring case, there was only one neighbor. In a more arbitrary case, there may be a certain number of neighbors that a given node is connected to. So, in the case of the so-called heartbeat algorithm, you send information to your neighbors, and you then expect information from these neighbors. Okay. And this kind of thing you continue until something comes out true. And it is called heartbeat because there's a certain rhythm here. You send, and then it comes back. You send, and something comes back. Whereas in the so-called probe and echo, we are limiting this to one specific neighbor, and you will choose this neighbor in a particular way, and you then expect an answer from them. And the broadcast listen. Here, the connections are such that they are potentially connecting every process to every other. So you just broadcast, and depending on the broadcast primitive, this may involve any number of processes. And in our book, on the other hand, we are assuming a certain small number or fixed number of processes, and so on. But in real life, all these algorithms are real classifications of real life algorithms. Here, you expect to see two essentially parallel activities in your system. One particular class of threads or processes is doing this, broadcasting of stuff. Another class of processes is doing receive. And sometimes these algorithms are quite intriguing, and I want to show you roughly one algorithm each or so in the next few minutes. So the style of the coding for this is going to be somewhat different. Here is a famous algorithm used with Dijkstra and Scholzen. This is not in your book, but it is discussed in the notes section. In this case, we are not assuming that the processes are connected in a particular ring or whatever. We are assuming that the processes are connected in whatever fashion, including complete graph or whatever. Okay. On the other hand, the basic idea is the following. Suppose the network of these processes, suppose it is a tree. Okay. Then, how do we detect termination? So far we looked at how to do this detection of termination in a ring using a token. Here we do not have a token, but suppose we have a network that is like a tree. Then the root of the tree sends the jobs to its neighbors. It may have a certain number of children, and so on and so forth. If each of the child reports to its parent that it is done, and if this is done all the way in the entire tree, when the root finds that all its children are done, and it itself is done, then we know that it has worked, right? But if the network is arbitrarily connected, we do not have the spanning tree. We do not have the tree to begin with. So what this algorithm does is it constructs a tree based on the first few transactions, first few messages. Okay. A particular node thinks of its first sender as the parent. Again, remembers itself. And this is the basic idea to see, to remember in this algorithm. So, and note that, remember how the Prabhaker algorithms will be written. Now we are writing them on certain when this thing happens. So it should be the case that the processes are doing other things while keeping an eye on this, so to speak. So when you receive a message with a certain process ID, this is the ID of the sender. And if you have no parent so far, then you give yourself a parent. Okay? So that is the step where we are identifying our parent for the first time. Then onwards, the so-called DIN is a number of how many input messages that particular node received. And messages sent by others to it, asking it to compute something. So that count is simply incremental. Okay, and there's a similar count, namely D out. These are the messages that are sent by this node. And once we got this message, then we are of course doing some computation on this message. Okay? So that's what we do when we receive an ordinary message. But when you receive a message that is special, and the word done indicates that, so we are assuming that there is one special message. And along with that, instead of receiving the process ID, you will receive a count. So if, on the other hand, you receive the done count message, then you decrement the number of output messages you sent by that amount. Okay? Now, as a part of doing that computation, this process itself may choose to send a particular process that is connected to a certain message and its own identifier. Okay? And of course, this being one output message, it increments the output. Are we clear on the overall idea? Whatever is the network of processes, this is what they are doing. At all times, each of these processes is ready to receive. And it may receive a regular message or a done message. If it receives a regular message, it begins some computation. As part of that computation, it may decide to subcontract the work. And it may then send to a certain number of neighbors these messages. Okay? And of course, it is keeping track of the number of output messages versus the number of input messages. Okay, this is the setup of the problem so far, not the solution. The solution is on the next slide. Is there any question about this? Yeah.
So DOut is really just outstanding messages.
Outstanding messages that you have asked others to work on, but you haven't gotten the answers back yet, saying done.
What is counter?
Count is the message that you will receive when this particular message is the special done message. So you haven't seen in this slide here, you have not seen the corresponding send for this. You have seen the corresponding send for this and that receive. So it is through this that you somehow obtain one of these messages. Any questions about this? So whenever it is that you want to ask, are you done or not, you invoke this algorithm. Okay, and this is the termination algorithm. And since it is not in the book, I'll let you write it. ST as before stands for such that. By the way, in case not everybody remembers this, I have a collection of my slides, copies, and Xerox sheets. You're all welcome to borrow it. I hope we have at least 20 to 30 minutes for new problem solving. Okay. So here is the corresponding done message sent. So whenever a process discovers that it is now idling, it will do this, J, where J is ranging from 1 to all the processes, total number n. So except for its own parent, J not equal to parent. So you are accepting this one number out of this list. You are sending the count of messages that you received to the J process, the count of messages that you received from J to the J process over here. Right here on there. This is DIN was a private array, similar to DOut, private to each process, their own DOut and DIN arrays. Let me say that. DOut is one number, DIN is an array, indexed by the process number. This stands for number of input messages from this guy, PID. Okay. Note that this message was sent by this process, as in here, where ME stands for your own number. So, when an arbitrary process is idling, except for the parent, remember the parent is who? The first process which happens to give work to it. This is not the only process that gave work to it. Other processes also gave work to it. However, the first one to give work was recognized as parent. Okay? So we send all of them the counts that you have, and of course you then initialize it to 0. This is the reversal of FA. And then you are looking at your own count. The number of messages that you send out, which is the out, right? If that is 0, now you can tell your parent that all the jobs that you gave others are done, right? And you are doing this because you are done, you yourself. So now you tell your parent that you're done and you give the corresponding number to it. Okay, remember that parent was excluded from the above loop. So there we are. Clear enough in the algorithm?
That doesn't mean that this process is necessarily done, does it?
It does. Except for this root. Of course, root doesn't have a parent. So, when the root executes this, and it is returning a true here, then we are sure that the entire network is terminated. Not when an arbitrary process says it is done. We need the root to say this. And so in this algorithm, now let's list all our assumptions. There's no assumption about how the processes are supposed to be each other. Arbitrary connection. But there is, of course, an assumption that there is one root process that started the computation. And this root process, of course, therefore, doesn't have a parent. All others have parents discovered by the first message. Okay?
I have a question. Let's say that process number 1 is the root, okay? And process number 1 begins by sending process number 2 some message. So process number 2 now says process number 1 is my parent.
Right.
And sometime process 3 is going to send process 2 some message as well.
Now, how did process 3 get something?
Let's say that it was that its parent is a root as well. Parent is
It's also 1?
right.
Okay. Well, let me use some other color. Yeah, go on.
Okay. So in the
So a tree is now like that.
correct. Now in function am I done for number 2.
Uh-huh.
Okay, number 2 will go through. It will send number 3 the done message.
Correct.
What if number 3? Because we don't guarantee that number 3 is going to receive that done message at any particular time. What if number 3 sends number 2 some more work?
You could. Very much.
Okay.
That is possible. So in other words, at the end of doing function am I done by process number 2, process number 2 does not then refuse any more regular message. It can still obtain, it can still get back and receive a regular message.
Yeah.
Okay.
That was my question when I asked it. When it gets to the end of am I done, is it done? That's not something.
No, it is not done necessarily. When, okay, I think now I understand the question. When this routine is finished by an arbitrary process other than the root, and suppose this answer here is equal to 0, DLD is 0, so the answer is true here. It does not necessarily mean that this process is now never going to receive future work. At that moment, when this was executed, it is quote-unquote done, as in idle. Within a moment after this, it may receive another computation from whoever. And that is why it is only when this is true for the root can we say that the entire computation is finished, all the network is finished. And this is the real problem, as I discussed at the beginning. If you merely ask each of these processes, are you done? They may all kind of say yes, but there may be messages in transit that they will receive afterwards. So if you ignore the issue of how do they actually check it, the answer to the termination detection is this. All the processes are idle at a certain moment, and there are no messages in transit. That is the answer, of course. But the question is, how do we know that there are no messages in transit? We don't have a mechanism of globally testing all the channels. Okay, now I want to kind of switch gears and talk a little bit about how some of the exams of mine are structured. And I want to kind of go at a reasonable speed. Here is one kind of problem that occurs. And don't assume that because this has occurred a couple of times that there are no other new algorithms. The problem that I typically give is something like this. An algorithm that you are not expected to have seen. You have seen this one, of course, in one of the old exams. But you're not expected to have seen it. So here is some brand new piece of code. Maybe you were lucky enough to bump into it in the textbook or somewhere. But then the question is asking, is this or is this not correct? And a typical question also says, if it is incorrect, give me a scenario. Given that now you know this is a paper in one of the journals here, you then kind of know. But normally I don't tell you where it appears, right? So you don't know if I reproduced it as is or did I inject some kind of a typo into it or some real error into it. So how do you go about thinking about such a problem? I want to spend just a few minutes. Give me some ideas. First, you must observe the syntax of it, right? Such as the PV matching and how the increments, the PV, the V increment and the P decrement are happening. In this case, by looking at these two statements, you kind of guess that these two semaphores, A and M, must be what? Split binary semaphores, in all likelihood. Now that is at the moment an unverified hunch, hypothesis. And you need to double check this. And you find that the initial values are matching your theory, right? A is 1 and M is 0. So far so good. Then you want to make sure that every time you are doing a V operation, the corresponding value for the semaphore is indeed 0. Otherwise, we're in trouble. And so, this is one trick, one immediate giveaway. If you see an if statement where there is an exhaustive condition, and based on that, you are either incrementing this or incrementing that, it probably means there is a split binary semaphore. So, the overall point I'm trying to make here is that even though such an algorithm you may not have seen before, the idea behind it, you have seen it, and we have studied it some deep enough level in class as well as in elementary school. Okay? So don't be too startled if you see something like this. And there are several questions on conditional critical regions, for example. All right? And another group of problems is the following. I give a what looks like a physical scenario, such as cars pulling in for gas in a gas station, cars traveling on some bridge or an elevator, and so on. Frequently, you are confused, not this group, I don't know yet, but the previous one, are confused about modeling these real objects. Okay? So just for the sake of explaining this, let us do, say, the bridge problem. So the bridge was something like this. Let's even say that it is 2 lanes. So traffic traveling that way and there, and this direction on this side. And the problem was clear enough in saying that there is some kind of a sensor on each one of these entrances. So there is a sensor, say S1 there, and the sensor S2 there. Now I want to simply illustrate some real life problems that shouldn't be, that shouldn't worry you in a context like this. So, what kind of a sensor is this? Well, it's the kind that you see, for example, on real roads, one of these wires strung across that part of the road. So when your car goes on it, it detects this. And some students worry, well, the car has 4 wheels. Is it going to generate 4 signals and therefore you divide by 4 and all this? Well, assume that somehow this is solved. Right? Because, I mean, we cannot deal with this aspect of the problem. I'm making myself, I mean, there are some tricky things that are, I'm not trying to test you on that. Okay, so that is one. And the other thing is, well, I think I usually give a number like this. That being a bridge, there is a limit of load, 20 cars. And we want to make sure that no more than 20 cars are on the bridge at any time. Well, how do we stop these cars? Well, by putting in a red light at the entrance. Right? So, the moment you discover that the bridge now has 20 cars, what is it that you should do? You should turn these traffic lights to red. Right? Question people ask is, well, what if there is a car that already traversed S2? Well, obviously, again, this is not something that we can solve. If you want to, imagine that there are one of these tire puncturing barriers or whatever. See, this is the kind of thing that we are not worried about. We therefore assume in an unreasonable sense, the moment this is red, cars will all immediately stop. Okay? So all this is doing is, we want to make sure that the total number of cars, some cars A here, some other cars B here, A plus B, is less than or equal to 20 at all times. Okay. Now, let's now look at the modeling of this in terms of CSP. So far I described to you the hardware setup and some non-assumptions. And you do not have to reflect certain reality-oriented things. What is S2 in terms of CSP? Suppose we want, obviously we need to deal with CSP or later on whatever other language. We need to deal with S2 and S1 in a certain CSP sense. Right? And we ask you to write a program in CSP that controls this setup. Well, let's look at this light, L2. What should L2 do? It normally has some color, and we need to be able to tell it to become red, right? So even though L2 is actually this hardware that lights up, so far as we are concerned, we can think of L2 as some kind of a loop process that receives from somebody the color of the light, say C, and then it basically sets itself to that color, right? Right? That's the process. And from who does it receive? Well, hopefully in our setup, we make that explicit. That it receives this input from a certain process, X. So from X, it receives a number or a value like red or blue or whatever, and it sets the color. Now this is a model of the actual hardware. And we are writing it like so because this is the way we interface with that real hardware that sits there. Are we clear on this? Similarly, so this is our L2. Let me ask you to write S2. What is S2? Now remember, we are now writing it as CSP. No semaphores. Just as I modeled the real life light, traffic lights, as that.
Starts out at 0 and has a counter.
S2 is a counter. Remember what I told you? S2 is one of these wires strung across this half of the road, so that when a car goes on it, it generates a signal. And somehow it takes care of four wheels problem. Right? So S2 sends a signal to somebody, right? It sends to somebody something. When should it do this? Whenever a car passes. So that itself is an input from a car process, and we now send whatever number you want to send, or just a pass value. To who would you send? Well, again, you would probably name a certain process. And it is the business of Y to keep a count of whatever. This is simply saying it passed. I have now one more car. And again, this is a loop. Okay? Now, is this right to say a car? I mean, officially we should write car parentheses I ranging from 1 to whatever. Total number of cars in the world. Okay. So that is again a piece of hardware being written as CSP code. So the problem is really not asking you to do this part. This is assumed. Most real-life hardware devices that generate something in response to some hard real-life events are effectively non-terminating loops in CSP. Usually, the inputs to them are from somewhere, whereas the outputs are the ones that we are interested in. So, the problem here is to write this control algorithm CP that keeps a total count of the cars on the bridge. And so it keeps track of these messages being sent by the S2 and S1 and appropriately increments or decrements it. Right? And there are sensors on the departing end also in this problem. So we know when a car has gone. So this problem is fairly simple to solve. Right. Now, the elevator problem that also occurred a couple of times before is slightly, compared to this, is slightly more complicated. And that, again, was there a question?
Yeah, when you mentioned really to be strict, you should say car, so I, one to every car in the world. Are you going to grade strictification?
No.
Okay.
No. In fact, the only thing that I hope you will do something to not confuse is the bang versus query. Bang is output. Query is input. Think of it like this. Query is you're asking a question to somebody, so you want an answer. So you expect something from others. So if you confuse these two, unfortunately, even though it's one character symbol, there's nothing much I can do. But if you are still unsure, instead of bang and query, write the word output or input. Instead of query and bang, write those words, output. Output to this process, this, input from that process, and put it into the story. So, Other than that, no, I'm not too worried about the impact. Okay, the elevator problem is very real life in the following sense. A bunch of tunnels through which the elevators are running, and each floor has buttons to push by the users. There are typically 2 buttons, up or down. And in the elevator, there are buttons for every floor. And a good system displays on each floor where the elevators are. And within the elevator, it displays what floor you are passing. Okay. Typically, what do you mean? Well, you mean this. Given that this is, say, floor 2 and this is floor 1, as the elevator passes from floor 1 to 2, it needs to know that it is about to do that. So there is a sensor here that detects when the elevator is passing it. In fact, sophisticated sensors can tell you when it is going from 1 to 2 as opposed to 2 to 1. But if you set up your algorithm, you should know in what direction the elevator is traveling. So when the sensor says an elevator passed me, you know whether it is passed from 1 to 2 or 2 to 1. Okay? So that sensor is modeled roughly as before. Right? On the other hand, let's talk a little bit about the buttons, various buttons. What is the model for this? Again, this is a hardware device, and we want to think of it as a CSP algorithm. You have seen how I modeled enough things so far. No, that's a logical requirement. What do you do when you go to the elevator shaft? You just press the button, and if it is already lit, it shouldn't do anything. If it is not lit, it should now light up. And behind the scenes, something happens. So what is that? Huh? What is that? So this is an input from user. And then there is a local light that lights up, right? And then, what else? What else should it do? That's it?
When the car
Keep
arrives.
quiet? No. It should do a little bit more. I mean, as you all know, there is some kind of a computer system that controls the thing, right? It should output something to that, right? So some control process should receive this press signal. Now, this control process obviously is going to receive messages from a whole bunch of buttons. So we need an identity of this button, right? So whatever number. In general, a pattern, a CSP pattern is sent, right? So this is a loop again, right? And strictly speaking, user is again user I going from 1 to whatever. Total number of users. That's it, or something else?
Now when the car arrives, the light has to turn on.
Right. Now, when the car arrives, we better turn the light off. And of course, pad bar. Now this we could say is coming from our control process. Okay, so that's the model on the button. Most buttons roughly behave like this. So the problem there is, you want to send the nearest elevator to the right place. You don't want these elevators to keep on changing directions all the time. You know, if it's going this way, it should keep going that way until there are no more requests. Right? Otherwise, you wouldn't like your elevators. They're unfast. And when there are no requests at all, they should stop somewhere rather than keep on going. And of course it is, as you know, there is a small little computer system that runs these things. And we are simply asking that algorithm to be expressed in CSV.
All these logical things like the elevator keep moving when there are no requests, will you be satisfied how we...
No, those are usually described, some of them are usually described there, the others are given in an open-ended sense that, make it as realistic as possible. And obviously questions like that are not graded on either you get full score or you get 0. There's a range of scores there. Basically, we are looking more at whether you understood the CSV idea and less in terms of how sophisticated an elevator algorithm this is. In these problems, that is not the issue. Now, there are other problems, since I have a couple of minutes let me do this, but this is more aimed at later languages and less so here. The following problem occurred a few times. If this is a tree, compute the height of it, binary tree, let's say. Just compute the height. And the point of this is often whether you are able to use parallelism or distribution properly. This is obvious. I'm not assuming you cannot do this in Pascal. I'm assuming that you can do this in a normal sequential language. So the question is about how to do it in a parallel kind of way. CSV included in now. A simpler, an even simpler problem is sum up an array of items. All of these have appeared once or twice. I hope you have all seen the example. Other than that, I urge you to look at problems in the book. Do we need some kind of a review session before the exam?
Actually, some suggestions for the problems from the book.
Yeah, I heard the suggestion, and unfortunately my answer is this. The book has no bad questions. All of them are good. Now, you may be thinking that there are a whole lot of problems, but if you read it carefully, he was inefficient. He repeats these problems over and over and over. For example, there is a problem known as roller coaster problem. This appears practically at the end of every chapter. I mean, he's doing synchronous message passing in one chapter, asynchronous in another chapter, and in the synchronous chapter he expects you to do using synchronous messages. In the asynchronous chapter he expects you to do that. So if you take away the duplication of that sort, then pretty much one at the end, if you look at the problem at the end of one chapter, say 7 or 8, that's good enough. And I noticed a lot of activity on defining the predicate source. That is not the kind of question. I mean, that's good that you tried to do it properly, etc. But that obviously is not the kind of question I'm asking here in this course. Even though a certain amount of familiarity with groups, invariants, and predicates is necessary. The book uses it all over. But I won't ask a question like specify sorting. So, chapter 1, if you want to, you can skip the exercises of chapter 1. But if you did that, you probably won't understand what chapter 2 is talking about.